Hi everyone. So today we're going to start talking about rotational inertia, which is actually where it starts to get a bit complicated. I know you might already feel like, oh, it's already been pretty complicated, but yes, we have just hit the tip of the iceberg. All right, so looking at the following diagram, if you release the block simultaneously from rest, which block lands on the ground first? So what to know about inertia, the rotational inertia, it's going to be equal. Wow, that's a weird sign. It's going to be equal to the sum of all masses times where they are from the radius. So if this thing is rotating down, right, and this thing is rotating down, it's going to hit the ground. It's going to be harder to twist this one here than this one here. And the reason why this one's going to be harder to twist is because a lot of the mass is concentrated on the ends. And this one is not, the mass isn't concentrated on the ends, closer to where it's rotating. So the more that the radius is concentrated, more of the mass is concentrated towards the end, the higher the inertia is. The higher the inertia it is, the harder it is going to be twisted. So which one's going to hit the ground first? That's going to be the one on the right, okay? Because the one on the right is going to be easier to twist, which means it's going to hit the ground first. All right, so let's look at this other problem. Small blocks, each with a mass m, are at the end, at the center of a rod of length L that has negligible mass. So this length right here, this has negligible mass. Calculate the moment of inertia of the system at the center of the rod. All right, so let's look at part A. So again, we know that inertia is equal to the sum of all masses. Wow, why can I not do that one? The sum of all masses, okay, whatever, r squared. So we have two different points of where the masses are. One all the way to the left and one all the way to the right. So if this length is a length of L, that means this is a length of 1/2 L, and this is a length of 1/2 L. Okay? So let's find how much mass this first one has. Okay? So that has mass of just m, and the radius is going to be 1/2 of L. That's how far it is from the axis of rotation, 1/2 L. And this is going to be squared. So this is going to be m 1/4 L squared. Now the second one, that's the one to the right. So over here, it's the same thing. It has a mass of m, and how far it is, again, 1/2 L, which we found already is just m 1/4 L squared. So if we were to add these two together, because that's the total, we want the total, that's going to give us the total, this is going to be equal to 1/2 ml squared. Okay, and that's our answer. Now let's look at this one over here that's at a point 1/4. Okay, so this one might be harder to twist or it might be easier to twist. Let's see if it's going to be harder or easier. So part B, same thing. Inertia is equal to the sum of all masses times radius squared. If this whole thing is L, then 1/4, so that means it's going to be 1/4 L, and that means this is going to be 3/4 L. Okay, so let's figure this out. Let's do this one on the left first. So I1 is equal to the mass. The mass is just m. The how far it is from the axis of rotation, 1/4 L squared, and that's all squared. So this is going to be equal to m 1/16 L squared. Now let's figure out what the inertia of this one is from this rotation here. So I2 is equal to m, and this is going to be 3/4 L squared, and this is going to be equal to m 9/16 L squared. So what is this going to give us? If we add these two together, we get 10/16 ml squared. You can simplify this a bit. 10/16 ml squared. Right? Yeah. Okay. So that's how we're going to do this first one. Okay. Now, it's important. So different objects have a different amount of inertia. So this is many times just given to you. But the inertia of this object, what we call this is like a solid cylinder here, is equal to 1/2 mr squared. And many times this is just given to you. Okay, but this is a very common one, so maybe this is one you should memorize. But a lot of times things like this, the inertia of an object is given to you. Okay, so a torque of 12 newton per meter is applied to a solid uniform disk of radius 0.5 meters. Okay, so this is going to be 0.5 meters. That's the radius. Okay, causing the disk to accelerate at 5.7 radians per second squared. What is the mass of this? So something is making this twist with a certain force, giving it a torque of 12 Newton meter. So now what we want to find the mass of this. So again, we know that force is equal to mass times acceleration, and this is when it's linear. However, now when we want to find something that's rotational, instead of force, we're going to find the angular form of force, which is torque. Instead of mass, we're going to have that's when you're pushing something linearly. When we're going to, depending on the position of the rotation, the inertia can be different. So we're going to do, instead of mass, we have the inertia. And then we have the acceleration, which is alpha. Okay, so we know a few of these materials. We have 12 is the torque. Inertia is 1/2 mr squared, but r is given to us 0.5 squared. And the alpha, is alpha given us causing this to accelerate at 5.7 radians per second squared. So that alpha is also given to us 5.7 radians per second squared. So now we're going to do a little bit of algebra, and let's figure this out. So 12 times 2 divided by 0.5 squared divided by 5.7, and we get m is equal to 16.8 kilograms. Okay, simplifies to 17 kilograms, but that's how you do it. Okay, so again, I know this looks complicated, but we're going to be looking at these formulas. Remember, there's also another formula for torque. So torque is equal to force times radius times sine of theta. So you have to know which one to use. And a lot of it is based on the information that's given to you. Okay? All right, let's move on to the next problem. Find the cable's acceleration of the diagram to the right. Okay, so we're looking at this diagram. We see we have a cylinder here that also has inertia 1/2 mr squared. And now we're trying to find what this cable's acceleration is. So this is a little bit confusing because the cable isn't rotating. It has a linear acceleration or tangential. So we're going to have to figure that out. So let's see how we're going to do this. So we can find the torque of this. So if the diameter of this is 0.12 meters, then we know that this is going to be 0.06 meters. Or just try to get as much information as you can. And okay, knowing we have the force we're pulling this with, and we have the radius, maybe we can now figure out what the torque is. So we know torque is equal to force times radius times sine of theta. The force is 9 newtons, radius 0.06 meters, and then now this sine of theta. So this is the axis of rotation, right? This is where we're rotating. So if we draw a straight line from where that is, we can see that this is going to be a 90-degree angle. So sine of 90, which is just 1. Okay. Now let's put this into our calculator. And we get 9 times 0.06, and we get 0.54 Newton per meter. So now we have the torque, but that's not what we're asking for. We want to find what the cable's acceleration is. So we can use the other torque formula to help us out with this. Torque is equal to the inertia times alpha. Okay, and maybe this will help us. I think there are other ways of doing this problem as well, but let's just go with this. So we found the torque, 0.54. There's always another way. The inertia, 1/2 m, which is given to us 50 kilograms, r, which is also given to us 0.06 squared, and then alpha. We can find what alpha is. So let's find what alpha is. 0.54 times 2 divided by 50 divided by 0.06 squared, and we get 6 radians per second squared. However, we're not looking for alpha, we're looking for acceleration, the linear acceleration. So what we should know is alpha times r is equal to acceleration. So if we have 6, radius is 0.06, this will give us acceleration, which is equal to times 0.06, 0.36 meters per second squared. Okay, and that's how we do that one. All right, let's look at this next one. This one might be a bit difficult. Let's see. You're lifting an 800 Newton bucket, okay, 800 Newton bucket of water from the ground to a rooftop 78 meters above the ground. Okay, so we're lifting this 78 meters. Okay. What should the diameter of the cylinder's axle be in order to raise the bucket at a steady 2 centimeters per second when it's turning 7.5 revolutions per minute? Oh, man, this looks rough. 2 centimeters. No, it's going up 2 centimeters per second. Okay. So this is rotating at 2 centimeters per second. Oh, no, we want to raise it up 2 centimeters per second. Ooh, man, just woke up. I'm having a hard time. 2 centimeters per second. Okay. And when it's turning 7.5 revolutions per minute. Okay, 7.5 revolutions per minute. Okay, let's try to find this. One thing we know is we're trying to get this up at a steady 2 centimeters per second. So that means it's going with a constant velocity, meaning acceleration is equal to 0. Okay. Okay. So we want to turn this at 7.5 revolutions per minute. Since we've been doing everything in radians per second, let's just try to change that to radians per second. So, okay, so 7.5 revolutions per second, and let's change this to radians per second. So again, let's get rid of revolutions, put it into radians. 1 revolution we know is 2 pi, and then so this gets rid of that, and then let's get rid of minutes and go into seconds. 1 minute is 60 seconds. Get rid of that. Okay, so this is going to give us, let's put it into our calculators, 7.5 times 2 pi divided by 60. So it's going to 0.785. So 0.785 radians per second. Okay, that's how fast we want this to rotate. Okay, so we got that. We got this under control. And now we want this to go up 2 centimeters per second. So now what we should know is the velocity. So this is going up linearly at 2 centimeters per second, or sure, we'll just put it 2 centimeters per second. And then this is going, and then we want this to rotate 7.5 revolutions per minute, or 0.785 radians per second. So now I know that the velocity is equal to the angular velocity times the radius. So this is going to be 2 centimeters per second is equal to the angular velocity, and we know that's going to be 0.785 radians per second times whatever r is. So this is going to give us what the radius is. So I'm going to do 2 divided by 0.785, and then this is going to give us 2.55 centimeters. Okay, that's what the radius is, but we want to find out what the diameter is. So we're going to multiply this by 2, and then what we're going to get is 5.1 centimeters. All right. Now let's look at part B. I know it was a lot confusing because there's like so much information, you don't know what to use, and we don't actually need to use a lot of the information, but let's see. If instead the axle gives the bucket an upward acceleration of 0.4 meters per second squared, what should the angular acceleration be? Okay, interesting. What should the angular? So what we know is the upward acceleration, so this one is now going up with an acceleration of 0.4 meters per second squared. Now we want to know what the angular acceleration is. So again, not too much we have to do here. Let's look at this problem. So we know acceleration is equal to alpha times r. So acceleration is 0.4. Alpha, we don't know, that's what we're looking for, but we now know what the radius is, which is going to be, and since this is given to us meters per second squared, let's change this to meters. So it's going to be 0.0255 meters. Now, let's figure out what alpha is from this. Divided by 0.025. I'm sure many of you guys, when you're trying to do this, so 15.69 radians per second squared, you just got lost and confused, and that's understandable. It takes a little bit of practice to try to, there's so many new formulas and things like that, so it takes a bit of practice. So keep on trying with this. Even though I might have done it simply, just keep on trying, because there's a lot of formulas, there's a lot of things going on right here, right now. All right, let's look at this problem. A 15-kilogram bucket of water is suspended by a light rope. Okay, 15 kilograms. around a solid uniform cylinder of 0.3 meters in diameter. So that means it's going to equal 0.15 meters. Okay. With a mass of 12 kilograms. Okay, this has a mass of 12 kilograms. The cylinder pivots on a frictionless axle through its center. Okay, pivots in the frictionless axle through its center. The bucket is released and falls 10 meters to the water. 10 meters to the water. Okay. What is the tension in the rope while the bucket is falling? All right, so this problem is pretty difficult. If you can do this on your own, you're on a good. You're pretty good at this. So let's just first draw a free body diagram. So over here we know we have a force of gravity and we have force of tension. That's what we're looking for, force of tension. We know force of gravity is 150 newtons. There's also a force of tension over here that's creating the torque. All right, so let's try to figure this out. First, we know that torque is equal to, this is equal to inertia times alpha. Okay, we're not looking for alpha, we're looking for acceleration. And there's a little bit of a trick we can do with this. What we should know is alpha times r is equal to acceleration. If we know that, then we also know that alpha is equal to acceleration over r. And many times we can replace this alpha with a over r. So let's try to do something like that. So we know torque is equal to inertia, which is 1/2 mass, so that's going to be the mass of this one, because this is what's going to be rotating. That's the inertia. So this is going to be 12 times, and then alpha, instead of a, instead of alpha, I'm going to put a over r, and r is 0.15. Okay? The next thing that I'm going to do here is I'm going to change this. Nope. All right, so torque is equal to inertia, which is 1/2 mass. So the mass is the mass of the cylinder right here, 12 kilograms. And then this is going to be equal to mass times r squared, and that r is 0.15 squared. And I'm going to change this alpha to be this, a over r. So it's going to be a over r, which is again 0.15. Okay, and what I can do with this is I could get rid of this 0.15 and get rid of that. The next thing I should also know is there's another formula for torque. That's going to be force of tension times radius times sine of theta. So force of tension, that's what we're looking for. Radius, which is 0.15. And I'm not going to do sine of theta because that's going to be sine of 90 degrees. And that's just going to give me 1. So I'm just going to put it like this. Is equal to 1/2 m 12.15 a. Again, I could get rid of this 0.15 because they're on both sides. And now I can find that force of tension is equal to 1/2 12 a. However, we still don't know what a is, what we're looking for, or force of tension. So usually when you don't know two things, you need to do a system of equation. So let's find another equation where we can do this. So how we can do this is we can do force of gravity minus force of tension is equal to mass times acceleration, if we're looking at this free body diagram here. One thing that I like to just do with these kind of problems is whatever the direction of acceleration is, I like to make that positive. So I know this is going down this way, accelerating that way. So I'm going to make that positive. You can do it the other way, but it just becomes easier, especially when you're doing system of equation problems if you do it like this. So force of gravity, which we know is 150, minus force of tension, which we don't know. This is going to be equal to the mass of the object. This time that's going to be 15 times acceleration. So what I'm going to do now is I'm going to replace this force of tension, and I'm going to replace that with what we have here. So I'm going to substitute this and put it right there. Okay, so let's see. 150 minus, now 1/2 times 12, which is also 6. So let me I'll just put 6 here. 6 times a is equal to 15a. Okay, so now I'm going to put this over to the other side, plus 6a. So it's going to be 150 is equal to 21a. And now I divide both sides by 21. And then I get A is equal to 150 divided by 21. 7.14 meters per second squared. Everything's in meters, right? Yep. Oops, that's not the answer. We're still looking for, we're looking for the force of tension. So I guess I should have found that. But I could just plug it into this formula here. Force of tension is equal to 1/2 12A. So if I know that, force of tension is equal to 6. 1/2 times 12 is 6. Times A, 7.14. And then what do I get? 7.14 times 6. 42.86. 42.86 newtons. Okay? And that's what we get. So what is the time of fall? So I think for this one, this is pretty easy. I think we could just do kinematics because we have enough information. We know it's going to fall a displacement of -10 meters. We know it's accelerating downwards at a rate of -7.14 meters per second squared. We know it gets dropped, so it has an initial velocity of 0, and we're looking for time. So now let's find this. Displacement of y is equal to v initial t plus 1/2 ay t squared. -10 is equal to 0 plus 1/2 -7.14 t squared. And let's do some algebra. -10 times 2 divided by 7.14 negative square root of that, and we get 11.95 seconds. Whoa, 1.64. What, did I do something wrong? Hold on, let me do 10 times 2 divided by 7.14. Oh yeah, I did something wrong. And then we should get 1.67 seconds. Yep. So let me change that real quick. 1.67 seconds. While the bucket is falling, what is the force exerted on the cylinder by the axle? So this is where it gets a little bit confusing. Let's draw a free body diagram of this whole cylinder. So we see there's a force of tension here. We found that's going to be 42.86 newtons. We also know there's a force of gravity on this. That's going to be 12, so that's going to be 120 newtons. So then that means the axis, there's going to be a normal force that's holding it up going up this way. And that's going to cancel out with 120 and 42.86. So let's see what we get. 120 plus 42.86. And we should get around 162.9. Okay, 162.9 newtons. That's what's holding it up. Okay. All right, I know that was a hard one. We're going to do more examples like this on the next one. But keep going with it, and I know it'll start to make more sense. Thanks for watching, guys.